Welcome everyone, and thanks for tuning into our second Distinguished Lecturer Series seminar here at the Max Planck Institute for the Science of Light this term. I want to extend a particular welcome to our guests who have registered for this series and are joining from outside the Max Planck Institute. The DLS seminars are the main high-profile scientific event of our institute and is a means to engage the most important and influential colleagues in any area of the science of light. In the background here, you see the exciting range of speakers this term, including concluding with a talk by Nobel Prize laureate Donna Strickland in February. Last week, we kicked off the series with a great presentation on protein aggregation by Thomas Knowles from Cambridge. And today, it is my pleasure and honor to introduce and welcome Jelena Vuckovic, who heads the Nanoscale and Quantum Photonics Lab at Stanford University. As a native of Serbia, Jelena moved initially to Caltech to obtain her master's degree, and then in 2002 her PhD in both in electrical engineering. And apparently she took a liking to California because she only moved a short distance onwards to Stanford for her postdoc, assistant, associate, and finally also full professor of electrical engineering. But apart from California, she also seems to like Germany, because I saw that she held visiting positions at the Humboldt University in Berlin, the Technical University in Munich, and also with our colleagues at the Max Planck Institute for Quantum Optics in Munich. Jelena has received many prestigious distinctions. Amongst them were the Presidential Early Career Award, the Humboldt Prize, and as of this year, also the James Gordon Memorial Speakership from the Optical Society of America. Before we get started, two technical announcements. This seminar is recorded, so please be aware that by participating, you implicitly agree to this. And second point, your mics and cameras are turned off. If you have a question, please type that into the chat space, and we will then read out the question to Jelena at the end, preferably. But we can also do that in between if they're really, really urgent questions. So enough prelude, and over to the real event. Jelena, welcome again, and special thanks for getting up this early for us.
Thank you very much, Jochen, for the very kind introduction and for the invitation. And thank you for moving the seminar by 2 hours to accommodate my Pacific time zone. It's much more comfortable for me to give a talk at 8 a.m. than at 6 a.m. Again, it's a great pleasure to give a talk online, but as you heard from Jochen's introduction, I like Germany. I actually go to Germany at least once a year in normal circumstances. I think this is the first year in a long time I haven't visited. So hopefully things go back to normal, and I can also visit Erlangen sometime next year and see the labs and all the great work that you folks are doing there. Do you see my screen? Just to make sure before I start. Okay. So I will cover some of the recent activities in my group that I try to summarize under the title Scalable Photonics, and incorporate some optimization techniques and machine learning techniques that we've been using to build variety of devices and systems. But as you heard from the introduction, my group at Stanford focuses on both nanophotonics, classical photonics, and quantum optics. So I will try to go in both directions and tell you what we've been up to in both of these. But the common theme is using this variety of optimization techniques to build scalable photonic and quantum photonic systems. And I don't need to explain this to this audience, but you know that photonics has many applications, and these are some of the most active areas of interest right now in industry and also academia. Includes, for example, optical interconnects for data centers, variety of optical computing platforms, LiDARs for self-driving cars, imaging systems, sensors, then augmented reality glasses, and quantum technologies. And then for all of these techniques, all of these applications, as you know, we cannot really use free space optic solutions just because we're constrained by the footprint of a particular application, for example, footprint of the glasses, or footprint of a LiDAR system, which should be small and like other sensors in the car, which means that we have to focus on integrated photonic solutions. And the question is really, can we integrate a lot of photonic devices and components to build functional systems for a variety of applications that we discussed earlier on? So in order to answer that question, we can revisit state-of-the-art photonics, kind of mainstream photonics. Here I show some silicon photonic devices from a variety of research groups. And you all know that state-of-the-art photonics or mainstream photonics is pretty much bulky, right? The components are very large, tens of microns per component. It's very sensitive to fabrication, temperature errors, which is why people incorporate these post-tuning elements, such as heaters, in order to tune everything on resonance in a system. They're also designed by manual parameter tuning of few parameters, something that you learn in grad school, for example, that this could act as a filter, WDM component for optical communications. You just pick that from the library of known devices, and then you tweak few parameters until you build something that works well for your application. But that also implies that, you know, most likely majority of these traditional devices and components are not really optimal. And it also implies that we have limited functionalities because there is a limited library of devices that people have developed and that we learn about during our, you know, optoelectronics education. And finally, as a result of all of this, a lot of these photonic components are not really efficient. For example, people build this optical interconnect system between processor and memory. And then because of all of the losses in photonics, they end up with energy consumption that is on the order of picojoule per bit, which is the same that people can do with state-of-the-art electronics. And that beats the purpose of using photonics in some of these applications, because you are not really doing better than what you can do with other solutions, and you are occupying more footprint, right? So how do you bring that down? And a lot of this, for example, is a result of the fact that people use inefficient components inside of the system, or use a lot of tuning elements because components are so sensitive to fabrication and temperature errors. And finally, what came as a surprise to me, because I've been working on a more fundamental side of photonics basically since grad school, when I started learning more about what people are doing in industry and in practical systems, I was surprised to find out that even in commercial systems, people actually have, for example, couplers that have coupling efficiencies on the order of 50%, which means that you throw away about 50% of your input power just because you didn't really design components to be better than something that you already know. And that, of course, is really problematic, even in classical photonic systems. For example, optical interconnects, where you're trying to reduce energy consumption in data centers that are already swallowing significant percentage of our power. But also it's particularly problematic in quantum systems, where you certainly lose enormous amount of information. I mean, your information is stored in the state of single photon, and you're throwing out more than 50% of them just because you have coupling inefficiencies, and you are depending on the protocol also sacrificing fidelity of the system, increasing integration times, and limiting basically the scaling of the system. So you know, all of this is something that we've been concerned about in my group for a long time, which is why we've been wondering for now about 15 years or so whether we could design and make better photonics. And this was primarily driven by our desire to simplify our experiments and make them more scalable, and also, facilitate fabrication, because often, as those of you who do nanofabrication know, you go to the facility and you make chips and hundreds of devices, and then maybe one of them works. And that's, even for university research, really difficult, but certainly for scaling purposes, it's really difficult. So what we wanted to really do is design devices with better performance than what we know today, with compact footprints, robust to fabrication errors, temperature variations, which is of course very critical for scaling of the systems and integration with electronics, but also for yield of functional devices, even in university facility. We wanted to figure out how we can design novel functionalities without like trial and error or brute force search, and without manual parameter tuning, which is very tedious and doesn't lead to optimal solutions. And finally, maybe longer term, if we're thinking about designing systems that contain complex electronics and also complex photonics, can electronic circuit designer also design photonics without, having a PhD in optoelectronics? And this looked like a wish list or a dream about 15 years ago, but 7 years ago, we managed to basically develop a design method for arbitrary three-dimensional photonic devices, which was first outlined in this paper. And prior to that, we had done work in 2 dimensions, on 2.5D. But of course, as you know, for practical systems, you really need to capture behavior in all 3 dimensions. And this is what we managed to do 7 years ago. And from then, really, this work took off, because we are now able to design arbitrary 3-dimensional photonic devices by searching the full parameter space. And resulting structures are highly non-intuitive. And this is what makes also this very exciting, because it's a completely uncharted territory. And most of them really look like abstract paintings, like the one that is behind me on the screen. But it turns out that apart from that aesthetic aspect of these devices, many of them, actually pretty much all of them, perform state-of-the-art devices in terms of the footprint or robustness to errors or energy consumption, and all the figures of merit that you set up during the design process. So we refer to this process as inverse design in photonics, because what we're doing really is defining what we would like to do, what kind of mapping between input and output we would like to do, and then design this black box. I'll describe that process in a moment. And we also incorporate into figure of merit whatever efficiency and robustness we would like to have, and so on, and wavelength range of operation. And this is a field of research that is rapidly growing. So we wrote a review paper 2 years ago with Alejandro Rodriguez from Princeton. And if you're interested in learning how people now are thinking or applying inverse design, you can actually check out this reference, which is still up to date. But the bottom line is pretty simple. Actually, what we're really doing is combining high-speed electromagnetic solvers with basically variety of optimization techniques. And that way we can design this black box to do particular input to output mapping. So for example, here we're designing a mode converter, first to second order mode converter between input and output waveguide. What we wanted to do is design it in a footprint that is only about 2 by 1 micron. And this is many orders of magnitude smaller than traditional way of performing mode conversion, which is adiabatic mode conversion, where to achieve greater than 90% efficiency, you need to do it over hundreds of micrometers on a chip in a waveguide. Here, we wanted to do it with greater than 90% efficiency in a 2 by 1 micron footprint. And when we start this, we picked some footprint, which is much, much smaller than the traditional one, but we didn't really know whether there was a solution. So you run optimization, and if there is a solution, you basically end up in some local optimum, and you stop when you satisfy figure of merit, which again includes efficiency and robustness to errors and so on. And I should point out that although you see 2-dimensional plots here, all of these optimizations are fully 3-dimensional. We just constrain the pattern in 2D plane because that's simple to fabricate. But if you can fabricate arbitrary 3-dimensional structures, you can actually optimize the pattern in 3 dimensions. So here you see the first phase of optimization, which is just where you allow your refractive index to vary continuously between limiting values in this case being silicon, which is black, and air, which is white. And then you end up with a solution for electromagnetic field on the right. But that, of course, is not something that you can fabricate. So then you go to the second phase of optimization, which we refer to as the binary optimization, where you basically then design something that you can fabricate and incorporates constraints and everything. So here is the pattern layout that you're designing. And on the right, you see how, as you're designing, as you're traveling through this enormous parameter space, you're also producing, converging towards the electromagnetic field that you would like to have. So full optimization of this device, which takes about 400 iterations, takes about 1 hour on gaming GPUs. So we don't really use supercomputers or scientific grade GPUs. We just use gaming GPUs that cost about $1,000 to $3,000, depending on the model. And you basically see here that these 400 iterations take a lot of electromagnetic simulations, because at each iteration step, we also have to do 2 electromagnetic simulations to calculate gradients on the figure of merit, so that we can actually propagate in the right direction in the parameter space to search solution. And in order to do that, we have to also develop very fast electromagnetic solvers. Otherwise, we couldn't really do 1,000 electromagnetic simulations in series in less than an hour. So that is part of this whole thing, like fast optimization and fast electromagnetic simulations. And we think that we can actually speed this up further. We have done some work on combining these fast electromagnetic solvers with neural networks to basically train electromagnetic solver to pick the right basis to solve the problem. And in some preliminary examples, we see 10-fold speed ups. So maybe the full optimization could take about 6 minutes instead of an hour for this particular device. And you may wonder why we're actually bothering with that. I mean, being a research group, I think this is very important, because here when you start doing the process, you actually don't know if there is a solution to your problem. So you want to have a feedback very fast. You don't want to wait 2 weeks and then realize that maybe you cannot design that particular device. We're independently working on the problem of finding bounds of functional devices. For example, whether there is a footprint, what is the minimum footprint for a particular functionality. But of course, that is a pretty difficult problem and something that we don't have a solution yet in general case. So I think we really need to do this kind of sometimes trial and error in terms of picking a footprint for a device for a particular figure of merit, and then seeing whether it converges and then restart the process, which is why speed is really important. And also doing it fast means also that you can scale it more favorably to larger footprint devices that are necessary for more complicated functionalities. I should also point out that, just highlighting how suboptimal traditional photonics is, we have found about 6 solutions in this footprint with the same efficiency for this mode converter. And that's, again, 3 or more orders of magnitude smaller than traditional solution, which means that traditional photonics is highly suboptimal, because you can find a lot of good solutions when you search the full parameter space. And this is just a very simple example, but of course, then you can change how you would like to map input to output and go to many other devices. Here is, for example, wavelength splitter, where you split 2 different wavelengths, 1.3, 1.5, in a also small footprint, 2.8 by 2.8 microns. You see here how the optimization process looks like as you are going to converging towards something that performs this particular function. Again, here there are multiple solutions in this footprint with the same efficiency. Here is one that you are looking on the screen as the optimization is proceeding, and there is another one for the same problem, which is behind me, which we fabricated and characterized, as I show you in a moment. And something like this, again, takes about 3 hours. This is slightly bigger device on gaming GPUs. So now going to final result. Here is one of the solutions that we made. Again, you're designing a 2-dimensional layout, but then you are making this in thin kind of silicon on insulator in 3 dimensions. So 3-dimensional design is incorporated. And you're performing 3-dimensional design basically as you're doing optimization. Here are fabricated devices. These ones we fabricated at Stanford in our nanofabrication facilities. And then the same device superimposed with electromagnetic field pattern. And here you see how, as you're changing wavelength at the input, your electromagnetic field first changes. I mean, first 100 nanometers are going to one output port, the other 100 nanometers of the bandwidth are going to the other output port as desired. This is what you designed it for. And then we fabricated a lot of devices, we measured them, and here is the measured result for many devices on the chip. Here we just directly plot transmission characteristics for all of them on top of each other, and they basically perform the same. And we did the same for 3-channel wavelength splitter, and again, measured them and they perform the same. And I should highlight that this is without any post-fabrication tuning, which we normally have to do for photonics that we fabricate. And this was fabricated in our university facility. Simply, we incorporated minimum feature sizes for our fabrication and our typical fabrication errors. So without any tuning knobs, heaters, or so on, they all performed the same. And working on this for a long time, we developed this software suite, which we call SPINS, Stanford Photonics Inverse Design Software, which now some companies and also academic groups and government labs are using. It can be licensed out of Stanford Office of Technology Licensing, both with academic or commercial license. So people are doing that. And we also have an open source version on GitHub. This is a basic version, which we call SPINS B. It doesn't have all the features of SPINS, but a lot of academic researchers are also playing with this basic version, and it's fully open source and contains electromagnetic solver as well. So now, this is how we started, but once it took off, we started applying it to a variety of different problems. Apart from these wavelength division multiplexers and demultiplexers that we started with, we've also used it to implement stage of on-chip laser-driven particle accelerator. I'll show that a little bit later. We also used it for non-reciprocal pulse router in silicon. And we've also shown that this is fully compatible with inverse design, with foundry-based fabrication. So you can use inverse design photonics in foundries. And these examples are all in silicon, but later on I'll show you also our work on diamond and silicon carbide. Clearly, this is just a design process, so it's agnostic relative to the materials platform. And as long as you know material properties, minimum feature sizes of your process and so on, you can translate this to any material that you work with. So now, just showing that it's compatible with foundry-based fabrication, which I think is critical for building systems containing a lot of different components. Process is pretty simple. You just design something by incorporating fabrication constraints for a foundry. And then you produce a layout that you send to a foundry, and then foundry basically just checks that whether it satisfies their design rules, and then sends it and fabricates the chips. So it's basically the same as what we do with e-beam lithography at our facility, but it's just done by UV lithography or deep UV lithography in a foundry. So here are some examples of our initial work with a foundry called AIM Photonics. AIM Photonics is a silicon photonics foundry in upper state New York in the US. So this is the first one that we worked with, and we collaborated with John Bowers on this from UC Santa Barbara. But since then, we worked with other foundries, Global Foundries, IME, and so on. So here is our 3-channel wavelength splitter made at Stanford, 3-channel wavelength splitter made in foundry, theoretically predicted behavior, and then experimental behavior for that, and again measured for many devices. And these are foundry-based devices, and they all perform the same and line up on top of each other. Then here is another one, spatial mode splitter converter. You split first order mode, send it to one port. This is about 2.8 by 2.8 microns footprint. Second order mode is converted to first order mode and sent to the other port. We fabricated cascade of these two in a foundry. This is theoretically predicted behavior. And this is important for, again, optical interconnect systems and capturing both polarizations from the input fiber in order to increase the capacity, communication capacity. And here is theoretically predicted behavior, and this is the measured behavior for many of them. And they all line up, again, on top of each other without any post-tuning. It's a very large bandwidth. Operation bandwidth is about 200 nanometers. very good contrast. You are not really routing your signal to the wrong port. That's what this contrast here means. And also loss is 1.5 dB per one device, which is comparable to design where we predicted 1 dB per device. And that small difference comes from the fact that we thought that minimum feature sizes of 80 nanometers would work. And actually there were more around 100 nanometers. So there was a little bit of the difference there. And just to give you an idea that you can scale this up, this is our work with Firuza Flatouni from UPenn and John Bowers from UCSB. These are optical interconnect systems for chip, and this involves a lot of chip-to-chip interconnects and on-chip interconnects, and this actually involves a lot of electronics as well. Here we implemented inverse design multi-mode multiplexer, demultiplexer. This was fabricated in IME, another major foundry. And we measured devices at Stanford, and it's actually excellent performance, telling you that this is fully compatible really with practical systems and foundry-based fabrication. So apart from just, compacting footprint and increasing efficiency for some components, I mentioned at the beginning that this is also very useful for implementing new functionalities. And now I'll highlight this with two examples. One is this non-reciprocal transmission and routing in passive silicon photonics, which is an important problem because, as you know, in a lot of photonic systems, you have to block reflection, use an isolator to block reflected pulses from going to a laser or your source, or you actually need to use some circulators or switches to route your back reflected signal and send them somewhere to a detector. So if you're making something like a LiDAR or integrated photonic system, you don't want to use an off-chip component, which is very large and bulky. And we wanted to implement this same function for some set of applications by using same silicon chip that you're using for your photonic processing circuit. And here we collaborated with a group of Andrea Lu from City University of New York. They had a very nice theory proposal a few years back explaining that this non-reciprocal routing could be achieved by combining two different resonators with different frequency response. One is Lorentzian, one is Fano. They're also nonlinear. You have nonlinearity in Fano resonator, and you control phase delay between them. And in this case, if you design the system in such a way that you couple different amount of power in your nonlinear resonator in forward and backward direction, what will happen is that you will have different frequency shift of your response of your Fano resonator. And that also means that at the frequency of your laser, you will have different transmission in the forward and backward direction. And Andrea's group demonstrated this at microwave frequencies using off-the-shelf microwave components. But doing it at optical frequencies was difficult because you have to design these elements with the right transmission characteristics. And doing it by hand is pretty tedious and is very labor intensive. I'm not really sure if it is possible to do it with as high efficiencies as we managed to do it by optimization. But doing it by optimization is pretty simple. It takes an hour or so. So we started from the system of two racetrack resonators in silicon, and then just optimized coupling regions of these two through the waveguides until we achieved the target transmission characteristics. Fano resonance with a particular response here, and then Lorentzian response here. And you see here how the optimization process looks like in these movies. They are designing pretty small regions, so that's why this doesn't take a long time. And when the optimization is done, these are the final regions, optimized coupling regions. So you're just optimizing coupler. You're not really affecting resonator. And these are measured transmissions for Fano and Lorentzian resonators, which match theoretical performance. And then when you measure fabricated devices, we exactly see what is predicted. In the forward direction, you always pass the signal. Here we're working with pulses. If you are in the right dynamic power range for the operation of the system, you're blocking backward propagation. That's in the yellow slots. So the reflected pulses are blocked from going back because they would just not be able to propagate because of the nonlinearity and the design of the system. And outside of the right dynamic power range, you are basically having both backward and forward propagation. We've also shown that this can operate at the speed of 10 gigahertz. In principle, even higher speed than this is possible because it's just limited by the nonlinearity and response of your system. So this is 10 gigahertz operation where you're blocking backward propagation and you're passing forward pulses. And this actually has practical applications. For example, for optical ranging measurements in LiDAR systems, you need to send forward pulses, and then backward pulses should not go back to your laser. They should actually instead be picked up and routed to a detector so that you measure delay between forward and backward pulses, and based on that, you do a ranging measurement. And of course, you can actually use a variety of switches, off-chip switches to do this with very high speed, or you can implement on-chip isolator, which people have been working on with magneto-optic materials or some dynamically tuned for larger scale photonic systems. But all of these solutions basically are having some issues, either in terms of losses, insertion losses, or switching time limitations, and so on. And in this case, for this particular application, we can achieve very high operating frequency, so we don't have a switching time issue. Footprint is very small, it's just another 2 resonators on the silicon chip, and insertion loss is only 0.17 dB. And indeed, we did actually 60-meter ranging measurement using this. We can discuss later in the interest of time. I will not really go into details. This is not really exactly isolator that would work for all the applications, but it works really well for a certain set of applications. So now the other application where we've been working on a new functionality is on-chip integrated laser-driven particle accelerator. Actually, this is a project called A-chip, founded by the Moore Foundation, and is led by Bob Bayer from Stanford and Peter Hommelhoff from Erlangen. Basically, this is the idea. The idea is very simple. The idea is to scale down large traditional accelerators just by employing different operating wavelengths, right? So by looking at the scaling between the typical microwave radio frequencies, wavelengths that are used in traditional accelerators, if you just use infrared electromagnetic waves to accelerate particles, you can achieve something like 4 orders of magnitude reduction in the size of the accelerator. But of course, the problem is that you cannot just take the traditional accelerator and scale everything 10,000 times down, because those radio frequency components are not going to work. And that means that you need to redesign everything by using dielectrics so that you can achieve acceleration. And we did implement this using inverse design. This project has been ongoing for more than 5 years, and there was also preliminary work in Bob Bayer's group about 7-8 years ago. But none of the solutions prior to this one had demonstrated accelerator that is scalable, in a sense that you can cascade multiple stages and go to larger energies of accelerated electrons, which is necessary in order to really build practical accelerators. And here we've shown on-chip integrated accelerator, again, enabled by inverse design. You see these non-intuitive patterns here. It's 30 micrometers long. We designed this element so that it can always accelerate electromagnetic fields coupled through grating coupler propagating here, would accelerate electrons that are incident from converted scanning electron microscope. And this non-intuitive structure here basically acts in such a way that it produces the field pattern that always accelerates electrons, which are incoming with particular energy. So that's 83.4 kilo electron volts in this case. The stage is 30 micrometers long. And here we use 2 micrometer laser wavelength for acceleration. And fabricated devices, some of them I showed on the previous page, previous slide. Here you see more of them: optical microscope images, scanning electron micrographs. This is all in silicon. And again, it's only a single stage. Here is the field pattern. And here is the experimental result. When you have no laser turned on, electrons that are coupled here to this vacuum channel just exit with the same velocity, with the same energy that they had at the input. But once you turn the laser on, you can accelerate them by up to about 1.5 kilo electron volts. which when you look at the gradient, and keeping in mind that this is only over 30 micrometers length, corresponds to acceleration gradients of more than 30 mega electron volts per meter. And that's comparable to really useful traditional accelerators. It also means that by cascading something on the order of a few hundreds or 1,000 of these elements, you can accelerate these electrons to mega electron volt energies, which is already useful for medical applications, for radiation therapy. And you can basically also obtain concentrated beam of electrons that could be used for targeted radiation therapy in tumor treatments, instead of having a very large beam of electrons that also irradiates healthy cells and healthy organs. So that's what we're working on right now. So this is just a single stage, just proof of concept demonstration. But what we're doing right now is trying to cascade hundreds or thousands of these elements to get to useful energies. And for that, we're also working with commercial foundries, because this is not something that we think we should be doing at a university facility. So now let me spend the last part of my talk kind of switching gears and talking about quantum optics. I said at the very beginning that my group works on both classical photonics and quantum photonics, and the common theme is this inverse design right now. But you know very well that there is a lot of activity in quantum science and engineering right now across the world, and a lot of initiatives. And there are also some interesting results coming out from industry. This is from IBM. There were also results from Google, and there is a startup in the US called Rigetti who work on superconducting systems, and they managed to scale them to about 50 qubits, which is maybe at the cusp now or doing something that we cannot really do classically. But certainly there has been a very remarkable scaling effort in superconducting systems lately. And then, of course, in atomic physics systems, people can do quantum simulators with hundreds of atoms or even 1,000 atoms. This is from the group of Emanuel Bloch at Max Planck in Munich. People are actually already for a number of years have been doing quantum simulation that cannot really be done classically. And that's, of course, quite exciting, but scaling is also difficult, especially in this traditional atomic physics way, because the setups are quite complicated and involve a lot of components and elements. And what we're trying to do in my group at Stanford, like in a number of groups around the world, is basically answering the question whether we could build semiconductor quantum simulators and computers, which means using a semiconductor chip such as diamond or silicon carbide, those are the materials that we're working on at the moment, to replace some parts of these systems and make them simpler. Of course, it's not just a chip. There is always an infrastructure and lasers and electronics around it, but it's much simpler than these atomic physics platforms or even superconducting platforms in terms of scaling. And for those of you who are maybe not working on quantum optics, I should just mention that for us, these quantum bits or qubits are optically interfaced semiconductor spin qubits. My group has done a lot of work in the past on semiconductor quantum dots, indium arsenide, gallium arsenide quantum dots. Physics is exactly the same. The reason why we shifted to color centers is because it is, as I mentioned in a moment, easier to scale up on-chip systems consisting of a large number of elements, which is what we're working on. But if you're more familiar with superconducting systems like the ones on the left, I should say that the physics or equations governing color center, which is quantum emitter for us inside of something like a diamond cavity or silicon carbide cavity, physics of that is pretty much the same as the physics of Josephson junction inside of a microwave cavity. Of course, we work at optical frequencies. Systems for us are smaller by a factor of 1,000 or more. So we have to use more sophisticated fabrication techniques than people implementing superconducting qubits, where everything operates at microwave frequencies, so they can use traditional microfabrication, and it's easier to make all the elements the same. That's harder for us, and we also have to deal with a lot of materials issues that I'll mention in a moment. But there are advantages, and I think working with semiconductors is an advantage. In particular, silicon carbide is a semiconductor that is already heavily used in power electronics applications. There is a possibility of operation at higher temperature, not at room temperature for what we're interested in, but still you can operate at few Kelvin as opposed to millikelvin, which means that you don't really need to use dilution refrigerator. And that makes experiments simpler and more scalable. We already have excellent photonic interface for our systems, which means that we don't really need to do quantum transduction from microwave to optical frequencies to build quantum internet. And quantum transduction is one of the burning questions in building superconducting systems and scaling them, because that it would not really be possible otherwise to connect these systems over larger distances and do distributed quantum computing. And finally, maybe most importantly for some of these systems, they're projected to have the number of 2-qubit gate operations per electron spin coherence time, which is larger than for superconducting qubits. They're very fast, gates are very fast, and spin coherence times can be pretty long, which means that you can do more operations before system decoheres, which eventually, when the systems scale up, means that you can make larger depth quantum circuits. So where do we stand in terms of this? We primarily work with diamond and silicon carbide. I'll mention that in a moment. And we use color centers in both diamond and silicon carbide, and we combine it with this optimized photonics on both platforms. First, in diamond, we're primarily focusing on group 4 inversion symmetric color centers, such as silicon and tin vacancy. This is just 2 missing carbon atoms and 1 extra impurity of silicon or tin in between them. And state of the art for this particular color center is that people have already demonstrated excellent photonic interfaces for silicon vacancies in diamond. There has also been demonstration of 2-qubit interaction at Harvard. This is for 2 color centers inside of the same cavity, which were favorably basically positioned and also detuned from each other so that people can tune them with the same external magnetic field, but of course not a scalable demonstration, right? But of course, I'll show you some ideas how this could be scaled further. But anyway, people have shown that 2 qubits could interact with the same cavity. And also more recently, there has been a lot of activity on tin vacancy color centers in diamond, which promise all the benefits of silicon vacancies with operation at slightly elevated temperatures. And slightly elevated temperatures here means few Kelvin as opposed to millikelvin, which is unfortunately needed for silicon vacancies to obtain the best results. And also tin vacancies have higher internal quantum efficiencies than silicon vacancies. So that's also favorable because you basically have work with the brighter quantum emitter and you have more scalable system. These results that I'm showing here are from my group's work for tin vacancy. At the same time, when we did the spectroscopy, there was a work done in parallel in the group of Mette Tature and Dirk England at MIT and Cambridge, confirming also agreement with theory. Very recently, we've also been able to incorporate tin vacancies in fabricated devices, and we've shown that there is no degradation in their properties, even in optical devices and relatively close proximity to surfaces. We see line widths of 36 megahertz, which is comparable to the best measurements in bulk diamond. So that's great. That's the reason really why we want to work with these inversion symmetric color centers, because they're immune to proximal surfaces, something that is very difficult to achieve in nitrogen vacancies in diamond. I mentioned in comparison with superconducting qubits that there are a lot of material science issues that we have to deal with, of course, when we work with these systems, because you want to selectively incorporate single color center or quantum emitter at the desired position. And that's something that we've been working on in collaboration with material scientists actively. For diamond, we've been collaborating with the groups of Nick Milosh and Ziyak Shen at Stanford. And of course, the burning question is how do you incorporate them at the desired positions and have exactly one quantum emitter at the desired position and so on. And this is something that had not been possible before, because to incorporate them, people would typically use high energy electron beams or ions, and in order to bombard diamond and incorporate these impurities at the desired places. But then it's very difficult to mask the material, and also this high energy implantation damages diamond, and that way introduces additional broadening and degradation of the properties of the color centers. And recently, to overcome that, we've come up with this shallow ion implantation and subsequent diamond overgrowth method, where we dramatically reduce the energy for implantation from hundreds of kilo electron volts to 1 kilo electron volt, which means that you can also use very simple mask, single layer resist mask. You bombard high purity diamond with these ions. That incorporates them at the desired positions, but of course they're at shallow, they're positioned very shallow relative to the top surface, which is also not desired for final devices, which is why we end this process with overgrowth of another high quality diamond layer. That way you end up with your color centers deeply embedded inside of the structure. And we've shown that with this, we can grow them at desired positions. We have very excellent properties. We eliminate some additional peaks that are a result of damage of the material, and we have much narrower line widths than when we work with high energy implantation. So that's kind of solving one part of the problems, and we're very excited about it. And apart from diamond, as I mentioned, we also work with the silicon carbide color centers, and in silicon carbide, we primarily worked with silicon vacancy in silicon carbide, which is produced by kicking out silicon atoms from 4H silicon carbide lattice by irradiation with electrons or ions. And here we've been collaborating a lot with the group of Jörg Rachtrop in Stuttgart, which has done pioneering experiments on this particular material, and also Sophia Economou on theory side from Virginia Tech. And here are some of the spectroscopy measurements from this particular material. You also see very good stability of color centers over hours of time scale. And it also has favorable energy level structures for a lot of interesting proposals, including some cluster state generation. People have demonstrated indistinguishable photon, single photon generation, very narrow line widths, long electron spin coherence time in this particular material. And silicon carbide is, of course, a lot of kind of common semiconductor material, which is why we're also very excited about this. But then going back to the question of material science, we and others have to spend a lot of time, and are still spending a lot of time, addressing material science issues such as inhomogeneities in qubits. And of course, for any scaling of quantum systems, these inhomogeneities are a very big problem, because if you have discrepancy between their transitions, this is it is very hard to build systems consisting of hundreds, or who knows, eventually maybe millions of qubits. And that inhomogeneity could also be seen in our measurements. These are spectral measurements for silicon vacancies, which are showing inhomogeneous broadening of about 30 gigahertz, much smaller than for indium arsenide, gallium arsenide quantum dots that we used to work with, but still pretty important and significant, something that we need to work on. And then also, you know, despite our methods for position growth, there are always some inhomogeneities. In spatial inhomogeneities, we can never have really perfect yield of one quantum emitter at the desired position with these methods. And that's why we spent a lot of time handling inhomogeneities. Apart from the improving materials, we also developed methods for tuning these quantum emitters onto each other. For diamond, we use Raman scattering. We drive each quantum emitter with a laser beam, which is detuned from the excited state transition. And then by changing that detuning, we can change the frequency of the scattered photon. Of course, something that people have been using in atomic physics for a really long time. But we've shown that by doing this, we can tune the scattered photon by up to 100 gigahertz, which is much more than inhomogeneous broadening of 30 gigahertz, meaning that by driving these quantum emitters with different lasers, you can basically interface them onto each other on the same chip. And in silicon carbide, you can use DC Stark shift, just put electrodes and then tune your color centers onto each other. We've shown that we can tune them by 200 gigahertz by putting electrodes. And also in that process, we're not really affecting these transitions and stability. They're still very stable and preserve excellent properties. Recently, we started going beyond just DC tuning of quantum emitters. We started looking into fast microwave driving in silicon carbide and flow-k eigenstates. This is interesting, not just for fundamental reasons. I mean, people have looked into flow-k eigenstates that occur in the quantum mechanical system with periodically driven Hamiltonian in atomic physics systems, but we've shown it in solid state, and I'll show you in a moment how this could be actually practically used to build more scalable systems. But in our recent work, we've shown also that under fast microwave driving for these silicon carbide color centers, we're able to observe these flow-k eigenstates of periodically driven Hamiltonian for a single quantum emitter. And then we went one step beyond, apart from just simple periodic driving to observe flow-k eigenstates. We started kind of motivated by our inverse design and optimization work, we started optimizing driving so that we changed the spectrum of these flow-k eigenstates. And of course, you can think about incorporating a lot of microwave harmonics until your spectrum at the output becomes asymmetric or obtains a particular shape that you would like to have, as shown here in these theoretical predictions. And then experimentally, when we do that, when we use some optimized microwave drive, we can completely change the spectrum of a silicon carbide color center. Instead of observing just two transitions that are signature of silicon vacancy and silicon carbide, with two color superposition, we basically obtain these four peaks in the spectrum, or we obtain this different spectrum for optimized microwave drive with four colors. And by changing this optimized microwave drive on different quantum emitters, we can interface them onto each other, making them talk to each other, because these different harmonics in their flow-k spectra can start interacting with each other, which is something that we're very interested in because it offers another knob to turn in terms of building scalable systems. So finally, kind of putting everything together, we have these qubits, we have optimized photonics, and where does that go in the future, right? And well, to build all the quantum technologies, quantum repeaters, networks, quantum simulators, computers, you basically need these long-lived qubits with good interfaces, but you also need efficient connections for these qubits. So I showed you how we plan to implement homogeneous qubits with optical interfaces, but then for the optical connections, we plan to combine everything with our optimized photonics, and we're already doing that in diamond, as you see here. These are diamond carved structures with some optimized devices, which are optimized using our inverse design, and we're also doing that in silicon carbide. And already in diamond and in silicon carbide, as you see in a moment, this is leading to significant improvements, at least in our experiments, simply by replacing some elements with optimized higher efficiency elements. Here we can improve signal to noise ratio for characterization of a single diamond cavity and reduce experimental time by about 500-fold, which means that it takes much shorter time to do integrate counts and hopefully to scale the system. And in silicon carbide, we're doing the same thing. I'd like to just remind you, if you're not familiar with silicon carbide, that silicon carbide is a material that is heavily used in power electronics. It's also available on wafer scale, 6-inch wafers in a bulk form. It's much cheaper than diamond, and it has excellent properties for photonics, including second-order optical nonlinearity, which we're very excited about. And these people are of course working a lot on lithium niobate and silicon photonics these days, but none of the other materials offers everything that silicon carbide offers, which is a scalable platform where you can also combine electronics, second-order nonlinearity like what you have in lithium niobate and electro-optical effect, but also offers quantum emitters that have high quality, as I showed you previously. So for that reason, since there is no commercially available thin film silicon carbide, we have to develop these thin films of silicon carbide ourselves. And we do that at Stanford. It's pretty simple. We start with bulk wafers, bond them onto oxidized substrates, and then thin them down until we obtain desired thickness. And here are the chips of silicon carbide on insulator, where we can make photonics. And at the moment, we're actually able to make very high quality photonics. These Q factors that we have at the moment are greater than 5 million. That's more than what we can actually see even in silicon when we do fabrication at Stanford. And loss is 0.08 dB per centimeter, which is comparable to foundry-based nitride, silicon nitride. And also we can combine this with inverse design photonics. In our first work, more than a year ago, we demonstrated second harmonic generation with efficiency of 360% per watt. Again, it's a second order or nonlinear optical material. This should be updated. We're actually updating performing experiments, but we expect this to be around 36,000% per watt because of the improvement in Q factors that we have, which is already comparable with leading nonlinear optical materials. And we've also demonstrated optical parametric oscillation with low thresholds. This doesn't involve quantum emitters, but it's of course very interesting for a variety of other applications in metrology or generation of entangled photon pairs. We've shown that this could be done in silicon carbide devices. And very recently, we've also shown soliton frequency comb with very low thresholds. So it's a very remarkable and respectable nonlinear optical material, which also hosts quantum emitters, which is how we ended up initially being interested in it. And of course, the ability to do nonlinear optics on the same platform means that even if you work with optically interfaced spin qubits and quantum emitters, you can actually do all quantum frequency conversion on the chip, or you can also do nonlinear based of optic parametric down conversion based sources. And for interfacing with quantum emitters, we've shown that we don't really sacrifice the properties of quantum emitters once we make silicon carbide photonics. So these are just very simple light matter interaction experiments where we tune quantum emitter silicon vacancy and silicon carbide onto a resonance, and we show enhancement, significant per cell enhancement. So now, just to close with the outlook, where is this going? I said we want to implement chip-scale quantum networks in simulators, and I think that this is possible. Of course, the solutions that I showed you would imply that you have to tune every quantum emitter with a separate electrode or with a separate laser in order to build a practical system. And probably with that, we can go to something like 20 qubits or so, which is not very useful. But I think there are solutions that can enable us to go beyond 20 qubits without the need to drive each one of them with a separate electrode with a separate laser. So we started wondering whether we can make this simpler, instead of having a separate electrode driving every quantum emitter or separate laser driving every quantum emitter, can we apply a single global drive on all of them, which kind of makes them talk to each other, even if they're inhomogeneously broadened. And that brings me to what we're actively thinking about now. I tentatively named it quantum inverse design. There's a lot of overlap between this and quantum control where we're now, but we're kind of planning to expand that beyond typical quantum control ideas, which design just pulse sequences for the system. Just summarizing our photonic inverse design. Photonic inverse design is essentially a fast electromagnetic simulator, which is coupled with optimizer. And that designs your photonic device to do particular function. Now we would like to do the same for quantum hardware design, where you have to couple an open quantum system simulator with an optimizer. An optimizer is the same optimizer as what you have for photonic inverse design. And that we think will enable us to start from the desired Hamiltonian of the system and achieve it by optimizing both driving of the system and also geometry of the system. And this work is led by my PhD student, actually, who just recently graduated, Rahul Trivedi, who in fact is moving to Munich in about a month to continue working on related ideas with Ignatius Iraq. So here are some of our preliminary results in that direction. How can we use these optimization techniques to make our quantum hardware simpler? So we looked into the idea of quantum transduction, microwave to optical quantum transduction. Typically, people think about the ensemble of quantum emitters to do that transduction, where you drive them with both microwave and optical frequencies, and that leads to mapping between microwave qubit to optical qubit. But inhomogeneity in that ensemble is what limits the transduction efficiency. So instead of tuning each one of them with a separate electrode or laser to collectively couple them, we thought whether we could optimize our driving on the system in such a way that we improve transduction efficiency and recover super radiance in the system. And our theoretical results indicate that this is possible. In fact, this degradation in transduction efficiency that occurs as a result of large inhomogeneous broadening can be recovered by optimizing driving on the system. This could be laser driving or microwave driving on all of them. And it's the same set of electrodes on all 10 emitters together. So basically, we see improvement in transduction efficiency of about 10 to 20 for random system of quantum emitters, which is quite exciting. And we're actually looking into doing this experimentally. And another idea is multi-emitter cavity QED. I said that the state of the art for two color centers coupled to cavity is coupling of two of them to single diamond cavity, work that was done by Michel Lukin and Marco Launcher at Harvard, where they tuned them with the external magnetic field, but that's of course not scalable because it depends on where emitters are and where their frequencies are. We looked whether we could scale this up for now to 3 emitters, but of course you could do it for more than that, even 10, like in the previous work on transduction that I showed, just by applying a single global drive. So you put single set of electrodes on these inhomogeneous emitters, you know where their transition frequencies are. Can you recover super radiant behavior and collective coupling to a cavity? If they're just inhomogeneously broadened, you measure transmission, there is nothing interesting going on. There is a cavity resonance and 3 transitions for emitters. But if you modulate all of them with the optimized drive that we found, then you can recover this strong coupling. And that is very exciting for us, again, because that means that with simple configuration, you can scale systems up to larger number of qubits working together. To summarize my work and my talk, I really believe that optimization, photonic optimization, is really crucial for implementation of scalable photonic systems, both for classical and quantum applications. If you're interested in playing with our software, you can download open source version, or you can also license the full version from Stanford if you're interested. We've used this to implement some new functionalities, including laser-driven particle accelerator on a silicon chip and non-reciprocal optical ranging measurements. We're actively using it in both diamond and silicon carbide to scale systems up. And in diamond and silicon carbide, now with all the developments on the materials side and with combination of these optimized photonics and qubit developments, I think that we will see scaling of these systems to larger number of qubits on the same chip in the context of quantum simulation or quantum networking. And that should not happen too long in the future. And with that, let me just finish by acknowledging our funding and collaborators, and also my team at Stanford. And I'd like to thank you all for listening.
Jelena, thank you very much for a really fascinating insight into your work. So thank you very much. There's not a lot of applause that can be heard right now, but I'm sure everyone agrees. There are also a number of questions. I'm going to read them out now. So one is, since you are leveraging Chi3 or nonlinearities in the non-reciprocal isolators, I'm assuming that the device is intensity sensitive. Does it require a threshold power for operation?
Yes. There is what I was referring as a dynamic power range. Yes, there is a range of powers in which it works. So definitely there is a sensitivity in terms of the input power, but it is a pretty broad dynamic power range of operation. Yes. Okay. And we did the detailed analysis of that in the paper. Having that said, you can design it for particular dynamic power range that works for your applications. And it's a pretty broad range. So if your power fluctuates, you still do see the same behavior.
Mm-hmm. And second question here is it compatible with data rates above 10 gigahertz?
Yes, so we did demonstrate 10 gigahertz operation. So the high-speed measurements that are also in our paper are 10 gigahertz operation. We showed that we have transmission forward, backward blocking at 10 gigahertz. We only had the equipment for 10 gigahertz operation, but it should actually work at higher speeds, also 30 gigahertz. But we didn't really have a pulse generator for 30 gigahertz to perform experiments.
Mm-hmm. And the final question then here is whether CW input is also supported.
CW for the isolator? That's a very interesting question. I mean, these are we did also some analysis of that, but in general, use is not really you can add additional components so that you can implement isolation. And actually, there was an interesting work from Pascal de Hey on cross phase modulation to support continuous wave isolation using resonators. And not in these resonators, different type of resonators. So that could be combined with our work to support continuous CW operation. But as of now, it's not really supporting CW operation because it will saturate the system. It only works in the pulse regime. And there is a limit also that we derive in the paper. I mean, it can work in quasi-CW regime because as long as your pulse duration is comparable to delay between the two resonators, in that regime, you can still operate. So by increasing the delay between the two resonators, you can kind of increase the pulse length for which you are operating the system. And that's because clearly, your pulses are at front or back input. And they don't really meet at the same time inside of your structure. But with that, still, you cannot really go to kilohertz. Maybe you can go to megahertz operation. But again, combining with some of the other ideas from other groups like Pascal de Hayes, you can actually completely shift this to CW operation.
Yeah, you know that Pascal is in Erlangen now, right?
Yeah. So you're colleague.
I think we have a choice to make because we are beyond an hour already. We have about 10 more questions. So the question is whether we want to discuss any of them in detail or if you want to go a little bit faster and maybe tighter.
I can try to answer faster. People are, of course, very welcome to send me an email if they have additional questions. Yes.
Yeah, okay, that's also great. But so the next question was related to the tin-based quantum devices, whether there's spectral diffusion in the photonic waveguides.
14 vacancies. Yes, we do see some spectral diffusion, and actually our recent, this is 14 vacancies in diamond, right, Johan?
So, yeah. I mean,
yes, so our recent paper from ACS Photonics studies that there is some spectral diffusion. We're actually looking into that, and we do think that some part of that could probably be addressed with the right type of driving, having some additional laser, above band laser or so on, which would affect the system properties and stabilize it, which people do with all the quantum emitters. In fact, we'll be talking also with the group of Ron Hanson from Delft about that because they also see some similar results. So there are some spectral instabilities, and if you're interested in detail, just look into our ACS Photonics paper.
Okay.
From this year, yeah.
Yeah. So Nicolas Joly has a question on the accelerator device. If I understand properly, it's designed for a given electron energy, right? So
yes.
Therefore, scaling up also means that each stage must be adapted to gain energy.
Yes, absolutely.
Yeah. So how about the fabrication tolerance at each stage, and how much could you expect to scale up?
I think realistically, since we rely on these optimization techniques for each stage, I mean, design is not very difficult. Adjusting design for larger input electron energy. I think realistically we can scale to something on the order of a few hundreds of these devices, which maybe 1,000, which still means single silicon wafer, few centimeters of a silicon wafer. That we're at the moment started working with foundries on basically implementing these structures. So we're still studying their fabrication constraints and tolerances for implementing these particular photonic structures, and we have to rely on a foundry to do that. But assuming all goes well, and we always redesign it for their fabrication constraints, I think we can get to mega electron volts in a reasonable amount of time. And then going beyond that, I think there are other issues that we have to deal with, which is materials damage. I think that's basically the main issue that we have as of now, because the powers that we can work with are limited with damage inside of the material itself. And we have to stop before we start burning our photonics, right? Because you have to work with high power lasers. So we've been redesigning photonics to minimize hotspots and damage on the couplers and so on. And there is more work that could be done there. But I think ultimately we're limited by materials damage. And that's what that means in terms of the energy of electron. I think we'll get to mega electron volts, and then beyond that, we'll see.
Okay, so then we have a few questions on the inverse design. Do you think it would be possible to extend this inverse design method from purely photonic devices to, for example, optoacoustic devices?
Yeah, definitely. I mean, you would need a different type of not just electromagnetic solver. I mean, keep in mind that now we just have electromagnetic solver. And then, of course, for quantum inverse design at the end that I was mentioning, we're working with open quantum system solver. So you just need to, for acoustic devices, you would have to build a new solver, right, that basically that doesn't just work only with electromagnetic waves, but you have to couple it also with wave equation for sound waves, right? But from the applied math or computational perspective, I actually view it as the same problem. Any eigen value equation could be solved by numerical methods and coupled to optimization. Mm-hmm. We are not really working on that, but I think it would be great if people take it in that direction, right?
The second question then, the patterns that you get appear quite random. Are you trying to make sense of the patterns and why they work so well?
Yeah. For some structures, we can make sense of them. I mean, for accelerator, of course, it's in this single stage periodic, and you understand why things look like the way they look at some level. For some wavelength splitter devices, like the one behind me on the Zoom background, it's harder to make sense when you just look at it. It looks completely non-intuitive. You can always make sense, if you backtrack the field profile and overlap with the refractive index of the underlying structure. And we're now actually looking into this a little bit deeper, like looking into pattern of the structure and pattern of the field, trying to make more general answer to that question, not just device by device, because I think it would be helpful in terms of initializing optimization better, right? So understanding of why things turn out certain way is going to be helpful in speeding up optimization and initializing optimization process. We have some intuition, but nothing that can be generalized to some particular answer that I could offer, right?
Yeah. So another question on the patterns was, you said that you find a local maximum or even several. So how do you know that you are, is there a global maximum? How would you find that?
Yeah, so these are not global optimization techniques. Of course, there are some global optimization algorithms, but the ones that we use are essentially gradient descent based, which means that they are only local optimization. My first answer to that is, in general, we don't really care if it's global optimum or if it is not global optimum, as long as it satisfies figure of merit. In some cases, we've done extensive search. I mentioned that, for example, for these wavelength demultiplexers, we ran for many different initializations, found 6 solutions, analyzed the full parameter space. We know what global optimum is, and there are like 6 local optima that are sufficiently good for how we constrain the problem. But again, local optimum is good enough, assuming that it is satisfying your figure of merit. We're doing now more of applied math perspective studies of that in collaboration with Stephen Boyd from Stanford. How far are we from global optima? In general, we don't care if we get the right local optimum from the user perspective, but of course, from the math perspective or optimization perspective, you do care about that. So that's why we're collaborating with applied mathematicians and optimization experts on this.
Also, because you pointed out that you don't want to lose power, for example, right? So you do want to get to a global optimum ultimately.
Yeah, but we do generally constrain this quite a lot, right? So for grading couplers, we, for example, design them with 99% efficiency, right? Which means that the more you constrain it, the more likely it is that you are going to go to some global optimum. And of course, optimization takes longer. But I agree with you. I mean, it's always best to get to the best possible solution. But sometimes, if you actually are greater than 90%, it's already much better than the other things. Or you just constrain and wait, but you can never tell if this was a global optimum or just another local optimum. Yeah.
With time, I guess you could. Anyway, so I'm going to skip Masha's question because she has some extra time with you anyway afterwards. And Pshita, if I pronounce her name correctly, had a question already, so I'm going to skip that too because there are not too many. Alexander asks, are you planning to use machine learning for your optimization?
Not to replace the full optimization. Yes, please go finish the question. Yeah.
Yeah. So what kind of networks do you plan to use, and which role are they supposed to take within
so we don't really plan to replace the whole optimization with machine learning. For the devices that we work with, it is not going to be faster because parameter space is enormous, and we're primarily interested in the study of the full parameter space of fabricable devices. So we end up with enormous parameter space. So training a neural network to analyze the whole parameter space is not going to lead to any speed up. People have done completely machine learning based design of photonic devices. For example, there was very nice work on metal surfaces, but it's a design of a single element, which is much smaller parameter space than what we normally handle. The only aspect where I think machine learning may be useful for what we're doing is in finding the right basis for solving electromagnetics of the problem. So we still do gradient descent, and we have high-speed electromagnetic solver, but there may be a better basis to solve the electromagnetics of your problem. And since when you're doing optimization, you're hundreds of times solving pretty much almost the same problem. You do minor perturbation and then you solve it again. Along the way, you can train a neural network to on those simulations that are very similar to each other in order to recover the better basis for solving electromagnetics of the problem. And we had a paper last year which showed that doing that, we can find better basically do better than just known preconditioners. So for solving these large matrices that describe the physics of their problem. So we can kind of beat the traditional approaches for iterative methods in solving matrices, because solving electromagnetics of the problem is, again, inverting matrices. So we can do better than that by training neural network to tell us which basis to use. But we did it on very simple problems. So I can't really make a general claim, but I think there is that's a possibility that exists maybe in practical devices that we work on. We're working on it actively right now.
Yeah, I think a lot of people are working on machine learning integration. I'm going to skip another question, refer again to your offer to contact you by email to get to one question that will probably could be seen as like opening up more philosophical angle to this. Phil Russell says, so it seems that a blind watchmaker evolution in a computer is much better than at creating solutions to a complex problem than an intelligent designer, like a highly trained physicist. Is there any future for us, and will we soon be superfluous?
Yeah, definitely. That's a very good question. I think we're not going to be out of business anytime soon. I think this is making our lives easier and actually, opening up new opportunities for science and new experiments and new applications. But even if you have the best software and sophisticated software, you as a physicist need to understand what you're designing, right? And maybe this is something easier to train electronic circuit designer on doing than kind of with traditional approaches where they have to design the full photonic device. But someone who still has some physics background needs to define what you're designing, right? And that's what we call figure of merit. So you need to define what mapping you want to have between input and output, what kind of efficiency, what sort of constraints in terms of fabrication and environment. And you need to have knowledge of physics to do that. Yeah, it's not possible just to have computer scientists do that. And people who do this in my group, although some of them ended up being really good software engineers, they all still have physics or EE degree, right? You can't just get Stanford has great computer science students, but if they've never seen physics, they can't really, work on this. They would have to learn physics or electromagnetism first in order to do this. So the bottom line is this will make our lives simpler, so we can focus on more exciting problems than just designing devices. We can do more exciting and scalable experiments, but we still need to define what we're designing. We need to tell the computer what to design, and that requires physics knowledge.
Yeah, you're also trying to build supercomputers, right? So quantum
Exactly.
computers that then have more powerful algorithms and eventually will be superfluous. Scary indeed. Thank you very much for your presentation, for the very nice and great extended discussion. So thanks again for joining us today.
Thank you. Thank you so much for all the great questions. Thank you.
You know that there are still a few individual.
Yeah. There is a different link, right? So I should just disconnect from here and connect there right now, exactly. Right? Okay. Thank you. Thank you. I'll see you there in a minute or so. Bye.
Bye.